Right, Adrian, we're going to be learning about voltage and current, okay?
Okay.
You've been asking me about this, haven't you? Okay. Right, I want to show you a short video first, okay? So, the video's on here. I'm going to skip to the bit that I think is worth watching. There's this silly boy who's got funny hair.
So, wiring for a headlamp is hit the battery. Inside
Right, let's have a look.
It's made up of a battery, a switch, a wire going to the headlamp, and a wire from the headlamp back to the battery. Inside the lamp is a bulb. When the switch is turned on, the circuit is complete. An electric current flows and the light bulb works.
Right, so what's going on?
So a boy is switching a light on, and then all the electricity goes to the light.
Is that what you think?
Yes.
Okay, well we'll see what they say now. They do a little animation now, and I think they do a nice animation that helps us understand what's happening.
But you can't see electricity. So what's actually...
Where's the light?
Here.
Okay. Where's the battery or the cell?
Here.
Okay, that's correct. So, what are those blue balls?
The electricity.
So we'll say that's the electricity, okay? Why have the blue balls got these yellow packets?
Because they are nearly at the bulb.
Is that what you think?
Yes.
Well, let's see what the video says and I'll ask you some questions afterwards.
happening. An electric current is a flow of negative charge around a circuit. The battery's job is to give the charges energy and push them out into the wire.
Right, what does the battery do?
The battery help it to work.
It just said the battery's job is to...
Keep it inside.
You sure? We'll go back and we'll listen again, okay? Listen really carefully. These blue things, which you're calling the electricity, they're the charges, they're the things that carry energy.
It's a bulb. An electric current is a flow of negative charge around a circuit. The battery's job is to give the charges energy and push them out into
So
the
the
wire.
battery's job is to give all the electricity's energy.
Okay, and those, just see they're holding bags?
Yeah.
Those bags are the energy that they're carrying, okay?
Okay.
Right.
I thought
This
it was.
happens at the
I thought
negative
it was
terminal.
their eyes.
Imagine the charges are carrying bags of energy. As they pass through the light bulb,
What?
this energy
What are they doing as they pass through the bulb?
They giving all the energy to the light, so they don't go in the light, because was I taught, and they just give all the energy to the light, but
Right.
they don't go in.
So the electrons don't get used up. The charges don't get used up. But they drop off the energy at the bulb. Okay? They drop off some energy at the bulb. Let's keep watching. So, let's keep watching and see what happens.
is converted into heat and light.
What's this doing?
But the charges don't stop moving.
It's not
They carry
really
on,
what's happening.
making
It's
the
just a
way
way to
back
help you
the
think about
battery
it.
and completing the circuit. Electricity doesn't get used up.
Right, let's have a little look at this. They're moving there.
Because electricity, because it doesn't use up, because they don't have any batteries in, they can go forever and ever and ever and ever.
Is it? I think that the little yellow balls never get used up.
And me.
Okay, the little yellow balls never get used up. But they can drop off, like they drop off their shopping almost. They're dropping off their
Yes,
energy.
it's like
Where did they...
bananas, lemons, and yellow stuff, and then put it back in there. It looks like that, doesn't it?
I want to ask you a question. What has the battery given the electrons? What has the battery given the little yellow balls?
Here's the battery. So
Yeah.
when they go in there, they get all the power.
They get the energy, okay?
Yes.
And that's the yellow bags of shopping, okay? And what does the bulb do What do the electrons give to the bulb then, or the charges? What do they give to the bulb?
They give them their energy, but
Okay.
they don't go inside it.
They don't get used up. The electrons don't get used up. Right. Okay, that's good so far. Let's keep going.
Charges don't change as they go through the bulb. It's the amount of energy they carry which changes.
Right, we're going to stop there for a second, and now let's go to something else. Right, I have another thing to show you. Right. I want you to tell me...
Reb.
Wait a second. I want you to tell me what's current. What does current mean to you? What does current mean?
That the electricity never uses up.
Is it? Is that what it means to you?
Yeah.
Okay. I don't think that's what we mean by the word current. Let's get a couple of these words good now. Okay. If I've got a pipe, right, and in there I put some water, yeah, the water would flow out and come splashing out like this, right?
Okay.
Let's say I can fill one whole cup with water. Do you see where the water is? Okay. Let's say this is the water. Oops. I can fill one whole cup with water a second. One cup a
Doesn't
second.
matter if you go on the lines or miss parts, doesn't it?
Hmm?
Doesn't matter if you go off the lines or miss parts.
No, I'm not too fussed about getting it right. So I want you to imagine if I can fill one cup in a second, 1 cup per second. Okay?
What
Or 1 cup
Is
per
it
second.
her when Nala or Molly purrs?
No, I mean, if I'm handing out sweets to you and Lillian,
Okay.
and I give you 1 sweet per child, how many sweets do you get each?
1.
Yes, okay. What if I gave you 1 sweet per second? How many sweets would you get if we waited for 5 seconds? 1 sweet for each second. 1,
You will
2,
5.
5 sweets, yes. Now, what would you prefer? Would you prefer me to give you 1 sweet per second or 2 sweets per second?
2.
2 sweets per second. Because then, if you got 2 sweets per second for 5 seconds...
See, yesterday we got 3.
Oh, yeah, okay. That's because we had a snow day. What would happen if you got 2 sweets per second? If you waited for 5 seconds...
We'll get 2 sweets.
2 in the first second. And then 2 sweets in the next second. How many now?
4.
Yes.
And then 6.
Yes.
And then 8.
Yes.
And then 10.
So you
It's
get
like
10.
counting in twos,
It
isn't
is, yeah. That's sweets per second,
Why are
okay?
you going to say that?
Yes, well, that's very good. So, one cup per second.
Like 2, 4, 6.
I want to imagine now. There's this pipe here. This pipe. This is the pipe here. Yeah, it's a tube like this, and we've got one cup of water per second flowing through it. Yeah.
Okay.
Now imagine.
All the electricity, all the water will go in the cup and set for down, 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 down.
Okay. I want to just try a different idea now. Imagine this pipe. Now, if I put two cups per second down there, like 2 sweets per second, does that make sense to you? 2 cups per second
Yes.
flowing through this pipe.
It'll
Yes.
be 4.
Wait a second. 2 cups per second, right? Now, if I get this pipe and I split the pipe, so half goes this way and half goes this way, okay? If 2
It
cups,
means it's going really fast.
if 2 cups per second come down this pipe here, right? So 2 cups per second of water is going down here, right? Down here, 2 cups per second. How much comes down this one and how much comes down this one? If 2 cups per second goes down into here, and then it's shared out down this pipe, some goes this way and some goes this way. How much would you get per second here?
It goes that way. This one goes that
Some
way.
goes this way and some goes this way. How much would you get?
You'll get 1 each.
1 each, right? So what we're really saying here is we're saying this is called
But
Kirchhoff's current law,
You're
Adrian.
just guessing drops then.
Maybe. Let's talk about this now in terms of physics. What we're really saying. We're saying Kirchhoff's current law. Kirchhoff's current law says that the current entering a node, current in, will be equal to the current exiting the node. Right? So if you get 2 coming in and you've got 1 coming out there and 1 coming out there, 2 must be equal
Maybe
to 1
when we
plus 1.
maybe that's 2.
That's 2. So we're saying if you've got
Maybe
a wire.
when we finished, maybe when we did half of this, we can keep on watching the video and then come back to this.
Okay. Well, yeah, we'll do that. Let's just have a quick look at this. Kirchhoff's current law. Here is a node. A node is like where all the junctions meet. So you've got, let's say we've got some current going in there. Let's test if you've understood. Are you getting tired? Should we test if you've understood?
No, I'm not getting tired. I was just
Pulling
smiling.
faces. I want to check that you've understood.
Smiling.
I want you to pretend that 4 cups per second go in there. Yeah? Or 3.
That'll be 5.
Wait a second, wait a second.
Will it be 6?
Wait, I haven't asked the question yet. I think you're getting tired. 4 cups per second are coming down there. Like, imagine
That'll
4.
be 6.
I haven't asked the question yet. 4 cups per second are coming in this way. Yeah? What would happen if 3 cups per second went this way? How many must be going this way?
4.
Really?
So
4 go in.
it could be 2.
Wait, listen. 4 go in. 4 come in. 4 come in. And 3 are leaving this way. How many must be leaving here?
1.
1. There we go. 1 cup per second. You've actually just applied Kirchhoff's current law.
Yeah.
So you've shown that you've understood. You've understood how current gets divided in a parallel circuit.
It's
Okay.
still not working.
Let's just go back.
Yeah.
All right. Should we stop there then? Should we say goodbye?
No.
You want to do some more?
Yes.
All right,
Let's
we'll carry
go
on.
back to the video and go back to this. Oh, no.
Okay, we'll go back to the video then. Right, let's go back to the video and let's have a look. There. That one. Okay. So, stop the video. Start the video again.
Means that 6 million the current flows from the negative terminal of the battery through the switch and the bulb to the positive terminal. An ammeter measures the electrical current. It measures how fast the charge is flowing in units called amps. A current of 1 amp means that 6 million negative charges are passing through the circuit every second. Reading
As
off
he
the
is
bottom
doing
scale
this-
on the ammeter, the current is
Yeah, he's trying to count. So you know when we said
Counting in your head.
Yeah, he's counting the number of charges per second, or if you want to imagine like the number of sweets per second going through the tube, or the number of.
So right now, all of them are going to.
Well, you were getting 2 per second. 2 per second.
2 amps.
2 amps. Now let's have a look. If you get.
No matter where you put the ammeter in a simple circuit like this, the current will always be the same. When the switch is turned off, the current can't flow. A gap appears in the circuit, so the charges stop moving.
Right.
When you add more bulbs next to each other, it's called a series circuit. So what happens to the brightness when there's 2 bulbs in series compared
Let's
to 1?
just watch this.
If you put more bulbs in the circuit, do you think they'll be brighter or less bright?
Brighter.
Why do you think brighter?
Because one bright on its own is one bright.
Mhm.
Depends how much light is coming out of it,
Yeah.
and
If you get another one.
if
They'll
you
be
get
twice as much.
another one, they'll speed twice as much.
Okay.
So it'll go
Twice that. Okay, I understand where you're coming from, but I've got another problem with that. Remember, they got those yellow bags. So, before the yellow bags are the energy. So each when you had one bulb on its own, how much energy did that bulb get per electron that went through it? 2 whole bags, yes.
Okay.
How many bags of energy do you think these bulbs are going to get now that there are 2 bulbs?
2 bulbs will be like
There are only 2 bags of energy. So if they're going to be fair, how much energy will they give to each bulb?
1.
Right. So will the bulb...
One a day, one a time, one a time.
One each time they go through, yeah. So what will happen then, if you look, can you see how that bulb's a little less bright than that bulb?
Yeah.
Now if you added them together, they might be as bright as that.
Okay.
But because the bulb's getting less energy
But
each, they're
maybe
not
you
as bright.
could get one more, and maybe it'll be as bright as this.
If you put another one in, well, that's an experiment to try. I don't think it would. But
Maybe it'll be 10 for it to go like that.
should we continue watching the video now? Yes, let's do that.
The ammeter reading for this circuit shows that the current is now smaller.
They've slowed down.
This means the flow of charge is now slower. Less energy per
Why
second.
is it?
Do you notice how they're moving slower?
Yes, why are they going like this?
Not sure what you mean. Let me have a look.
Is reaching the
Look,
bulb.
can you see them? The packets.
Oh, I see what you mean. Yeah, they're sort of jiggling around a bit. Maybe it's just the animation. Okay. Look, 2 bags. See, they've got 2 bags. How many bags have they got now?
1,
How many bags have they got here?
0.
Right.
But when they go here,
So wait a second. How many bags have they given to this bulb?
but when
How many bags have they given to this bulb?
I don't know those two.
There's 2 there and there's 1 there. How many must he have given away?
There should be
How many bags of energy has he given away?
4,
Well, he's come in with 2 and he's left with 1.
3. 3.
If you had 2 bags in your hand
Okay.
and you went to someone's house
Joop. Go to
and
someone's
then
house.
and then you came out with only 1 bag,
Okay.
how many have you left behind?
1.
1. So they've left 1 bag in that bulb. Do you understand? They've left 1 bag in that bulb. They've dropped 1 bag of energy on that bulb.
Okay.
So the voltage drop, the energy drop on the bulb is 1 volt. Right. Now look at the second bulb. They came in with 1 bag and they left with no bags. How many bags did they drop on the bulb?
2.
They came
2.
in. Wait, Adrian,
Let's
listen.
just say
Wait,
2
they
a
look.
day.
No, look. They came in with 1 bulb and they're left with none. How many bags have they lost?
2.
They came in with 1. They've left with none. Did they have 2 bags?
So they gave 1 to this one and they gave 1 to this one.
Yes. So the voltage drop on each bulb is 1. Should we watch the rest of the video?
And then come back to the
Picture.
video again, okay?
So the charges now have to share their energy between the 2 bulbs.
Oh, why is it
Neither
going?
are as bright as one on
Right.
its own. What would happen to the current if you kept adding more and more bulbs?
Right. We'll leave that. We'll go back to this, and then I think we'll be nearly ready to finish this video. So let's have a little look at these 3 different setups. Okay.
Let me just.
Okay. Do we have a look at? Can we see this?
Yes.
Right. A
A.
in this one. Yeah.
That's
There,
starts
now,
with A.
let's just say you got. Let's just say we had two charges per second moving through here. Two charges per second moving through here. Yes. Are they faster or slower here, or are they the same?
They're faster there.
Are you sure?
And they're faster all the day.
They're the same speed all the way around, aren't
Yes.
they? The current is the same everywhere in a series circuit. Check this one out as well. Right? They're a bit slower in this one, aren't they? Can you see?
This is going fast a little bit on this. It's going a little bit slower.
Do you think?
Yeah.
I think they're identical. Look, if you put one extra in there, one extra comes out here. Every time one goes in there, one comes out there. Yeah? So again, it's a series circuit. The current's the same all the way around.
Okay.
Right, what about this one?
Wah!
Look, I think it's slower here than it is there. What do you think?
And me.
Right? If you look, imagine 4 per second go down here. And then they have to be shared. So 4 per second come down here, and they've got to go, some go down this way and some go down this way. If 4
Okay.
gets split into 2, what do you get? If you
Four
have 4
gets
sweets,
split
4 sweets, and have to share them with you and Lillian, how many each?
2. It'll
2
be
each.
2.
So 2 down that branch and 2 down that branch.
Nearly finished.
Now,
over there.
finally, let's just do one last little bit, okay? Came in with 2 bags, left with no bags. How much energy has it dropped on the bulb? How many bags has it dropped on the bulb? Just came in with 2 and left with
2.
2. Right. Came in with 2 bags, look. Came in with 2 bags. Came in with 2 bags. Left with 1 bag. How much energy was dropped on the bulb there? Came in with 2, left with 1. What's the voltage drop on that bulb?
Came with 2 and
Get your fingers out your nose. Came in with 2. You wanted to do this video. Came in with 2 and left with 1. What's the voltage drop on that bulb?
it'll be 1.
Okay. Came in with 1 bag. Left with none. What's the voltage drop on that bulb?
What did I say?
Came in with 1 bag. Left with none. What's the voltage drop in that bag?
0. 1.
1. Okay. Now look at this one. This is in series. In parallel, sorry. They've come in with 2 bags and they're left with
Oh my
none.
goodness!
They've left with none.
It's going fast here
Yes.
and going slow here and then going fast up.
Right, yeah, because what's happening is where it meets the junction here, the node, the current is splitting up and slows down. So if you had 4 amps flowing here, or 4 coulombs per second flowing through this bit, maybe you've got 2
Can't
coulombs per
block
second.
them, block them.
I can't block them, and 2 coulombs per second down this one, and they all add back up again to 4 amps down here, or 4 coulombs per second. Right, let's look at the voltage very quickly, and then we're done. Okay.
Okay.
So just check here, please. How many bags have they each got?
Just say
How many? Can you see where the mouse is? How many bags have they got?
they have 2 in each one.
Okay, and what about here?
They have none.
Right. So how many did they drop on the bulb then?
1,
No, they came in with 2. They left with none. How many did they drop on the bulb?
2,
2. What about this one here? They came in with?
none.
No, they came in with how many?
Where?
How many bags are they coming into the bulb with?
2,
And how many are they leaving with?
0.
Right. So what's they drop? How much do they drop on the bulb?
All of these are just 2, 0, 3.
All right. So what we've seen here is that the current in a series circuit is the same everywhere. So if you get 1 coulomb per second on this side, you'll have 1 coulomb per second everywhere in the circuit. Okay. In a parallel circuit, the current gets divided. The current has to add up to whatever's entering a node will equal whatever's leaving a node. That's just current law.
Okay.
With voltage, whatever the voltage drop across the cell that's powering or running the circuit is, it will be equal to the voltage drop across the components in the circuit, the components that are in series in the circuit. So you can think of it like this. Just to simplify the whole story, voltage in series is shared and current stays the same. Voltage in parallel stays the same, and in series the voltage is shared.
What does
Okay.
that mean?
Well, we'll come back for another video for another day. Okay.
Okay.
All right.
Maybe
Say goodbye.
tomorrow. Bye.
Bye.
Maybe tomorrow.
Maybe.
later.
So just very quickly, ammeters must be placed in series and voltmeters must be placed in parallel. Ammeters measure the current flowing through them, and voltmeters measure the potential energy difference either side of a component, and they must be placed in parallel so they can sort of check the energy per coulomb of charge on one side of the component and compare that to the energy per coulomb of charge on the other side of the component. In series, the current is the same everywhere in a circuit. So 2 amps comes in, it's 2 amps here, it's 2 amps here, it's 2 amps here. Everywhere in the series circuit, the current is the same, right? But the voltage is what's getting shared. 4 volts across the cell is shared 2 volts, 2 volts here. So the 2 volts and 2 volts add up to the 4 volts. In parallel, though, the voltage is not shared, it's the same. 4 volts, 4 volts, 4 volts. So if they left here with 4 bags of shopping, they go into here, they lose their 4 bags of shopping and leave with nothing. Similarly on this one. So voltage is shared out. Voltage is the same for everything in parallel, but it's shared in series. Current is the same in series, but it is shared in parallel. So to summarize, in series circuits, the current is the same everywhere. The voltage is divided though. In parallel circuits, the current is divided, but the voltage is the same everywhere.
Well, we'll come back for another video for another day, okay?
Okay.
All right.
Maybe
Say goodbye.
Bye.
Bye.
Maybe tomorrow.
Maybe.
We can